Hello everyone and welcome to this lecture. In the past lecture, we saw how we can solve a linear equation. That is, we saw if we have a differential equation of this form that is boxed with the blue color over here, let's call it 1. If you have a linear equation like this, we developed a theory and some formulas to find the solution for this linear equation. And if you recall that this mu was our unknown function with some c that was constant, and there was this exponential part where there is some integration, and finally using this mu we solved this differential equation over here, that is 1, and we found out that y of t will have some form like this. And today we are going to see an explicit example that how we can do it. So before I move on, I want to emphasize one thing, that is, you are seeing that mu of t is some c, then there is some exponential. Sorry, the integral will be over there, not over here. So because of this c that is a constant, you can get many of these mu's. That is, if you take c equals to 1, you can get some mu function. Let's call that mu1. If you choose c equals to 2, you get some mu2, and all of them are valid, but we are going to stick with the case where c equals to 1, because we only need one mu function, that is one of these mu's, to get our work done. So let me emphasize that we will take c equals to 1. So let's try to see an example now. If you take c equals to 1, then this mu of t will be just exp integration of pt dt, this guy. And now let's take an example. And this example will be a lengthy example because it will also show us if this equation is not in the standard form, that is on this form like 1, how we can make it into a standard form. That is, given the equation, you do some algebraic manipulation and bring this given equation into the standard form. Then you identify your p and q's, and then you go on and solving them. So our first example, and obviously the only example that we're going to talk about today, will be of the form some t square plus 1 y prime minus ty is equals to 2t t square plus 1 whole square. This is our equation, and there is some initial condition that when t equals to 0, y of 0 would be 2 by 3. So this is our equation over here, and this is the initial condition. Let's call it IC, that means initial condition. So how we go on and solve this, right? So the first thing we need to do, we need to bring it into a standard form. To do that, we want to divide this whole equation, that is this whole part, by t square plus 1. So let's do that. And the reason I'm doing that, because if you notice that y prime was just standing over there, but there was no guy onto the left or right, right? So that's the kind of form that we want to achieve. So to do that, just divide by t square by 1. So let me write divide by t square plus 1. If you do that, this will be y prime minus t divided by t square plus 1. Y is equals to 2t, and this is a t square plus 1 whole square, so that will be just reduced to t square plus 1, right? Now you can identify the p's and the q's. So let's identify them. This minus t divided by t square plus 1 is our p. So p of t will be minus t square plus 1, right? Because you can always write a plus over here, and this plus minus would mean a minus. So that's how this thing comes. And then your q of t is already apparent over here. This will be just 2t t squared plus 1. So So now what we want to do, we have identified our p's and q's. Now we want to identify our mu function, that is mu of t. This is the second step. The first step is to reduce the equation into the standard form. Once it's in the standard form, then you want to go and hunt for mu t. And if you recall that a few minutes earlier we told that mu of t will be just exponential, and in the exponent there will be pt dt. And note that this is an indefinite integration. So let's write this down. exp, our pt was t divided by t square plus 1, and there was a minus sign in front of it, right? This guy. Okay, so let's write it down. Minus will come out, and there is t square plus 1 dt, right? And this is a very easy integration, because if you take the denominator to be u, then the only thing you are missing on the denominator is just a 2. And so let me just give you a short description that what I'm going to do. There is t dt, and this is just t square plus 1, right? And if you just multiply and divide by 2 and consider t square plus 1 equals to u, then du is just 2t dt, right? So this whole thing becomes 1/2 of du by u. It's just some simple integration by substitution. So if you do that, that is if you just integrate this whole thing, this will be exp minus 1/2, because there's a minus over here, right? And this 1/2 is coming from here, that is du by u. And if you integrate du by u, that is just ln u. Obviously you can write the modulus sign, or you can choose not to write it as well, that is up to you. So this will be minus 1/2 ln t square plus 1. And you might wonder, why am I not writing a plus c, right? Because this is infinite integration. Another way we can justify this c equals to 1 is to actually take this constant that will come out of this integration over here and multiply with c and call it c prime, then taking c prime equals to 1. So that's another way to justify it. So at this point, don't be alarmed with these constants, and this is a way to justify that why I'm not writing a constant over here right now. So let's carry on. So this can be simplified further, because this minus 1/2 can sit over here. That's a property of logarithm. So this will be exp of ln of t square plus 1 minus 1/2, right? And exp of ln, that is exp of ln, meaning e to the power ln, let's say x over here, and this is just x, right? Using this identity, we can write it as t square plus 1 minus 1/2 to the power minus 1/2. So we are done with the first two steps, that is we found our mu of t, and we also reduced the equation into the standard form. The final step is just finding our solution, the desired solution y of t. And as you can see, I have already marked down the value of mu equals to 0 and y equals to 0. This will be useful later, because we are going to use this formula, this boxed formula. And you can also see that I have marked this thing as a c. That was a constant. And notice that in the past lecture we used some limits, that is I want to see my solution within some certain interval, that is something I'm taking on the direction of the independent variable. So we wrote it like, let's say from t0 to t. So this was the initial starting point, the lower limit. And for us over here, this t0 is just 0 for this particular problem that we were discussing. So using that formula, let's try to find the solution. So I write y of t, and 1 upon mu of t would be, mu of t is just t square plus 1, and we'll have a minus 1/2 then what we'll have is that an integration, and it will start from 0 because 0 is our starting point, that is the initial point, and we want to extend it up to t because there is no restriction on up to which point I want to see my solution. So that's why we're taking a general point and we denote it by t. And now we are going to use the formula above where you have mu of tau, because tau is now a dummy variable over which the integration will take place. So mu of tau would be just simply tau square plus 1 to the power minus 1/2, and then you have q of tau. So q was 2t times t square plus 1, and we want to replace with 2 tau square plus 1, right? And finally the measure, and here you will have your mu 0 and y 0. We already calculated mu 0 and y 0 was given to us. So let's go to the next line of calculation. So I'll just start from here because it will be a bit long calculation. So t square plus 1, there will be 1/2, and now we have to do this integration over here first because we already know these values. So let's try to do the integration. First simplify all the things. Let me write this thing line by line so that you understand better. So you'll have 2 tau and this guy over here. So let me just mark them with red colors. This guy over here and this guy over here, they will get multiplied with each other and the things will simplify. So the simplified thing is just square root over tau square plus 1, and finally we have our measure plus mu of 0 was what? 1, right? And y of 0 was 2/3. Okay, now what it remains is to just to evaluate this integration, which is pretty easy if you remember how to use integration by substitution. So this is just 0 to t 2 tau square root over tau square plus 1, then d tau. Take this tau square plus 1 to be u, so u is equals to tau square plus 1, then du is just 2 tau d tau, right? And this is precisely the integration that we have. So this will be, instead of integrating over u, you can just ignore the limit points right now and replace u later with appropriate limits for t. So our integration is just square root over u du, which is just u to the power 3/2 divided by 3/2, which will simplify to 2/3 u to the power 3/2. And now to get the right values for these limits appearing over here, you need to replace u equals to tau square plus 1, and you need to put these numbers over there. So after recalling this easy result from calculus, we now write our result as follows, that it will be 2/3 u to the power 3/2. So u was what? Tau square plus 1. So you have your tau square plus 1, and then you want to evaluate it in t and 0, and then finally you will have another 2/3 over here. You can take this 2/3 common or factor it out, whatever you want to say, and here you will have t square plus 1 minus, if you put 0 there is just 1, right? So finally you can write t square plus 1 to the power 1/2. You will have a t square over here, and this 1 and this minus 1 will cancel each other out, and this will be our solution. Oops, sorry, I think I missed something. So after doing this integration, we'll get these things, and obviously there is a power of 3/2 over here, and if you just do it, you can see that, oops, sorry, so when you do this integration at this point right here, you are technically done. Obviously you can simplify it further. That is, first you need to reduce it to the standard equation, then find the unknown function, and note that this unknown function is also called an integration factor. It's called an integration factor. Different literature interprets mu of t different ways, but this is a very common name, that integration factor. So you should know that. And this will be it for today, and I'll see you guys on the next lecture. Thank you.